All right, so this is the first of what is going to be a three-part series on how to do everything for the ECO329 final exam. This first session is just going to deal with one mean, one proportion, and one variance. And I think I was also going to do one other thing. I want to double check to see what that was. P-value, minimum sample size, one-sided confidence interval stuff, if I can get to that. So let's start with the one mean stuff. I'm going to be referencing questions from some old exams, as well as giving you guys the PDF for the exam review. So having that on hand is basically your instruction manual for doing all the problems of that type. One of the big things you're going to be doing, as I might have mentioned before, is that you're either going to be doing mostly confidence intervals or rejection regions. And so what I've given to you for both, I've given you both confidence intervals and rejection regions for one mean, one proportion, one variance, two mean, two proportion, two variance. And so those 6 types of problems each have steps to either construct a confidence interval or a rejection region. And so with that in mind, I'm going to be making sure that you follow those steps every single time to get an answer for that type of question. So we're going to start off with some one mean questions. We're going to start off with summer 2019, number 4. That question says, in many developing countries, people are increasingly using mobile money to make payments, so like Venmo is a good example. Because of cost of administering mobile money accounts, the profitability of mobile money as a line of business depends on the distribution of annual number of transactions per customer. This is the first paragraph, doesn't really have any numbers in it yet, but we're gonna keep reading. We work for a telecom company. We take a random sample of 41 customers. Cool, so they gave me information right off the bat. They've told me that 41 customers, so I'm going to say n equals 41. What I'm going to do is I'm going to skim through this problem and see where the first time that they mention any number, and also write down any relevant information, namely that they say at some point, a normal plot indicates the number of transactions is approximately normally distributed. So we're going to go ahead and put approximately normal. This isn't really a number, but the approximately normal bit tells us what part of the tree we're going to use when we suss out whether this is Z distribution or T distribution. The next thing says, in your sample, the mean annual number of transactions is 95. Now, some people either put mu or some people X bar, but make sure you pick the right variable here. It's really important that we don't say mu. This is from the sample. So this is not mu, this is X bar. The mean number of transactions from the sample is 95. The problem goes on to say, the standard deviation is 12. And again, this is from the sample, so we'll be using the letter S. So we've got everything we need at this point. And then in part A, we want to create the 95% confidence interval. So we're going to say CL equals 0.95. With that in mind, we're going to reference the cheat sheet that I've given you, and we're going to look at confidence intervals. The annoying thing is that the way I structure my cheat sheet is that I put the list of instructions for rejection region here. And so there's a box for all the steps for rejection region. And I put confidence interval here, and all the steps for confidence intervals are second. So everyone's really gung-ho about seeing the first thing that's on that page, which is rejection region, but we're not being asked to make a rejection region here, so don't do that. Skip down to the bottom part of the page for, this is one mean. Skip down to the bottom part of the page to see what the steps are for a confidence interval. Oh, and a few other things. Why do I know this is a one mean question? Well, they keep saying, calculate the 95% confidence interval for the population mean, right? And we're talking about the number of transactions. I might ask, how many customers or how many transactions does the customer make? That's the answer there is a number, not a yes or no question. So with that in mind, I know this is a one mean question. I'm not comparing 2 different groups. I'm not comparing people who live in Tanzania versus people who live in Mozambique or anything like that. This is just one population. Okay, so once I have all these numbers, the first thing I need to do, step 1, is determine whether it's Z or T. And the way we do that is by using that tree that we've seen so many times now. I'm going to draw it one more time, and I'll go ahead and quickly draw it. You can screenshot it if you want. If you're annoyed that this is the 3rd or 4th time you're seeing this, sorry, live with it. I'll make this. This will be the last time I draw this tree, though. So is the population normal? And the other questions are then, is population standard deviation known? And the last question down here is in large. So, and you go up if the answer is yes. You go down if the answer is no. The answer to the first question is yes, it is approximately normal. We were told that it was approximately normal. So we're going to go up this branch on the tree. Is the population standard deviation known? No, they didn't give us at any point in the question the population standard deviation. They only gave us the sample standard deviation. So the answer to this question is no. What distribution do we use if the answer here is no? We use the T distribution. If the answer to both questions are yes, we use the Z distribution. If the population is not normal, but the sample size is large, we use the z distribution, and we're doing that because the central limit theorem is allowing us to. So you might say z by central limit theorem. And if n is not large, but then the population is not normal, then you really can't do anything about it. So these are the 4 outcomes. For our particular problem, one more time, we were told the population was normal, so we went this way. And then did they give us the population standard deviation? No, they only gave us the sample standard deviation, so we went down here, and we're going to be using the t distribution. Okay. Might want to grab a calculator. Actually, I still haven't gotten my graphing calculator out. I'm still in the long process of moving. But, so I'm going to rely on you, Victoria, to get some t-scores for me. Of course, I can probably find it on the online if I have to. We need to get a t-score. So step 2 is get your hands on t-score. T is equal to inverse t of 1 plus your confidence level divided by 2, comma, your degrees of freedom. A couple things is, 1, make sure that when you're typing this into your calculator, you're putting parentheses around 1 plus your confidence level, because I don't want you to divide just the confidence level by 2. I want you to divide 1 plus the confidence level by 2. And degrees of freedom is your sample size minus 1. Did you already go ahead and grab that t-score?
Hold on. I'm currently looking for my calculator, actually.
No worries. I can also look up an inverse t calculator online, so I can do that as well. This would be 40 degrees of freedom. And I want a confidence level of, this is 95, it is 2.021 is what I get. So I'm just going to believe that that's correct. I don't think the calculator online is lying to me. Maybe it is. Hopefully it's not. So 2.021 is our t-score. Now that I have that, I'm going to go on to step 3, which just says construct the interval, which is x bar minus t times standard deviation over square root of n, less than mu, less than x bar plus t times standard deviation over square root of n, close parentheses. Your professor, if you were taking this on a blue book, she would also probably say, I want you to put c here and say this equals 0.95. So this is weird notation that she likes to use. But realistically, all your professor is going to ask for is what is the lower bound of the confidence interval, what is the upper bound of the confidence interval. So we have all these numbers. We have x bar, we have t, we have s, and we have n. So taking all these values and plugging them in here and here are going to get your answers. I'm going to go ahead and do that. So we're looking at 95 minus 2.021 times 12 over square root of 41. That comes out to be 91.21. 98.79. 98.79 for the upper, and then what I say, 91.21 for the lower. And this is your interval. So this is, I'm sure, going to be, this is probably the answer to one question, and then she'll also ask for the upper bound, because you can't type in an interval into Canvas, so she has to ask them, and you probably saw this on your quiz as well, she asks in order what the lower bound is, then followed by the upper bound. There's a good follow-up question that asks about, that I think is going to ask about the, oh no, I've lost the tab, there it is. Oh, okay, I thought this was going to be a minimum sample size, but we'll get there in a second. Your economic analysis suggests that in markets where the mean annual number of transactions is about 100, your company could increase profits by lowering the fee by making a payment, blah, blah, blah. Using the confidence interval for part A, test the null hypothesis. So now we're getting into hypothesis testing, which is good, because we will be doing a part 4. Part 4 wants you to test some hypotheses. And the way we say hypotheses are the null, which is denoted by H sub 0, and the alternate hypothesis, which is denoted by H sub A. We are testing, it says, test the null hypothesis that the population mean is 100. Okay, so we're going to write down mu equals 100. This is population mean, right? Test the null hypothesis that the population mean is 100 against the alternative hypothesis that it is not. So the wording that was used here was not equal to, so that means we're going to use, or was not, so not equal to. Of course, you could say test the alternate that it is greater than 100 versus less than 100. In this case, it said not equal to 100. So in our case, we're just going to say not equal to 100. And then step 4 says, on the cheat sheet, step 4 says, if you're ever going to draw a conclusion about the null hypothesis, you just check to see if the interval captures the null hypothesis, or captures the null hypothesis value. So we say, if the null hypothesis value is in the interval, we'll say in the confidence interval, then we accept the null hypothesis. And vice versa. If the null hypothesis value is not in the confidence interval, then we reject the null hypothesis. Now in our case, our null hypothesis value is 100. 100 is not in this interval. And because 100 is not in the interval from 91 to 98, we are going to reject the null hypothesis. And that's all there is to it for question number 4, both parts A and B. I'm going to add a follow-up question, which doesn't exist right there. This will also tackle minimum sample size. So a follow-up question could have been, what sample size, what sample size would be required to ensure the length of the confidence interval is no more than 4, okay? There is somewhere down below on the cheat sheet, so this is probably a few pages down beyond the one mean section, so it's a few pages down from this. You'll probably see 2 different minimum sample size questions. We're going to tackle only one type today. This is not the minimum sample size required to generate a certain value of alpha and beta, but this is the minimum sample size needed to guarantee a desired margin of error or desired length of an interval. The formula for a one mean case is z star times standard deviation, or it could be our sample standard deviation. We'll allow it for right now, over margin of error, and we're going to square that value and then round up. I want to point out that we are using z now. It's fine, but we're using z star now because we don't know the sample size. So we're going to use a z star for a 95% confidence interval. Again, this is still I'm going to remind you that this is still 95% confidence interval. With that in mind, I need to go to my calculator and find the z star for a 95% confidence interval, just like we did for getting the t-score, just like we did for getting the t-score right here. But we're not going to be using inverse t, we're going to be using inverse norm because this is a z. So you'll do inverse norm of 1 plus 0.95 over 2. There are no degrees of freedom for normal CDF or inverse norm, so it's 1.96 is the value you get out. This says sigma, and in light of not having any standard deviation, or at least from the population, we're going to be using the sample standard deviation. So this is going to be our proxy for the standard deviation. That'll go there. What is our desired margin of error? So Victoria, I will grill you on this one. One thing that messes people up is that she often says length of the confidence interval, which is fine. My formula uses margin of error, but the length of a confidence interval is just twice the margin of error. So in our case, what is our margin of error?
Were we just supposed to do like inverse norm?
For z, yeah, for the z, right?
Oh, okay.
But
wait.
Go ahead.
So you're asking like the length of the margin of error? Wouldn't that be 4?
So careful. So the one thing to think about this is, well, let's draw an interval. So if I say here's the interval, right? There's this distance and this distance. This is one margin of error down, and this is one margin of error up, right? You've probably seen polls that say plus or minus 2 percentage points or something like that, right?
Oh, okay.
So actually, let's do 3% because I don't want to spoil the answer. Plus or minus 3 percentage points, right? Well, that means if your interval is 3 points this way and 3 points this way, then what is the total length of the interval?
6.
6.
Yeah.
So that's the same idea here, is that this length they said is 4. So they're saying this entire distance across is 4, right? So with that in mind, what's our margin of error?
2.
It's 2.
2.
Exactly. So we'll just take the 2, and that's going to go here in for margin of error. So let's see if I can make some room here. Let's get rid of this and this. We have our z star, which is 1.96. We're going to continue using S as our standard deviation, 12. And as you said, the length of the confidence interval is 4, but that means the margin of error is therefore 2. Put that in, square that. So 1.96 times 12 divided by 2, and then squared gives me 138.29. But of course, with any sort of sample size question, you always round up. So the minimum sample size needed would be n equals 139. Any questions on that?
That's all good. I'm going to step away just for a minute, but
Sure.
I will be back.
Okay, you just let me know when you're back. I'll try and steer the ship by myself. All right. We're going to move on to number 5. We work at a telecom company in Tanzania. You want to estimate the population mean in distribution of amounts of money. So not the number of transactions, but now the amounts of money that are measured in shillings, which I guess is the currency there. A random sample of 500 transactions. So this is, a reminder, summer 2019, number 5. And we're now doing, we're just reading through the question to see what some of the numbers are. A random sample of 500 transactions. So I'm going to go ahead and write that down right off the bat. 500 transactions, the first thing they tell us. In a random sample of 500 transactions yields a sample mean of 20. So X bar equals 20. Going to continue. The sample standard deviation is 3.5. And they want the 90% confidence interval for the mean number of transactions. I want to point out that at no point during this problem statement did it say it was approximately normal. So at no point did they say amounts were approximately normal. Normal or approximately normal. We are missing that information this time. So with that in mind, when you revisit your tree, remember the first question is, let's see if I can actually undo this. No, I'm not going to undo it. I'm just going to say, the first question was, is it approximately normal? And the answer to that question is no. This time the answer is no, it is not approximately normal. So we're going to go down this branch. When we go down this branch, the question we are confronted with here is n large? And what counts as large? That would be n equals 30. So if it's bigger than 30, which this definitely is, we're up in the 500s, we then say, okay, we're going to use z, but we're using the central limit theorem to allow us to use z. The central limit theorem says that if you take a large enough number of observations, then you can use the central limit theorem to say that you're going to be using the z distribution. So with that in mind, we're going to be using z. Step 1 says, determine if it's, according to my cheat sheet, so we're still on the one mean page, is it z or is it t? Well, we've determined that we'll be using z because not approximately normal, but our sample size is large enough. So we'll say we'll be using z by CLT because distribution is not approximately normal, but our sample size is large enough. So with that in mind, we go on to step 2, which tells us you need to define what that z-score is. So the z-score is inverse norm of 1 plus 0.90 divided by 2. Don't need any degrees of freedom. When you do this, you get 1.645. I always go to 3 decimal places on this guy. So 1.645 is our z-score. Moving on, cruising on into step 3. This is where we're going to use the formula. So we're going to use the formula x bar minus z times standard deviation over square root of n less than mu less than x bar plus z times standard deviation over square root of n. Not much has changed here. I'm wondering if, okay. Not much has changed here. The only thing that's really changed has been the fact that we are now using z instead of t. Doesn't really matter too much. We're still using all the numbers we were given before and plugging these into, like, so do we have x bar? Yeah, it's right here. Do we have z? Yeah, we found that right there. Do we have s? Yeah, it's over here. Do we have n? Yes. So I'm just going to plug in all these things into my calculator to get an answer. We have 20 minus 1.645 times 3.5 over square root of 500. This gives me 19.74. And if I do the plus, I get 20.26. I'm rounding the 2 decimal places today, but that would be your answer. You're not being asked to draw a conclusion the same way we were for part B of the previous question. They just wanted to know what the endpoints were. That's it. Okay, let's move on to, we're going to do a 1 proportion now. Let's see if we can continue with this page here. I wonder if we don't have to go on to anything else. 1 sec. The one proportion question on this test is number 2. So I'm going to go up to number 2 and see if it's a good one to do. Okay, this is a good one. This is summer 2019. Number 2. I don't know why I put the pound sign over here. There we go. Okay, summer 2019, number 2. It says, you want to estimate the survival rate in West Africa during the outbreak of Ebola in 2014. As of November 11th, there had been 14,413 cases. 5,504 of them had died. Ignore the possibility that some patients subsequently may have died. Assume that 8,909 patients survived. Construct a 95% confidence interval for the true probability that a person in West Africa who contracted Ebola survived. So they didn't tell us, they told us a sample size right off the bat. They said that there were 14,413 people that had contracted Ebola. Is that number correct? 14,413. And that of those 14,413, 5,504 had died. They did not give us a p-bar, but they kind of gave us a p-bar. P-bar, which we don't have, is just going to be found by taking that 5,504 and dividing by the 14,413 that had the virus. So this comes out to be 5,504 divided by 14413, 0.382. Okay, so 0.382 is the proportion of people who died from Ebola. It's important to note that sometimes they want the, and this is the case for this question. This is why the question is tricky. This is the percentage of people who died from Ebola, but part A wants the confidence interval for the proportion of people who survived. So make sure you're paying close attention to this. This is why this is tricky. If I told you like 30% of people are married, but then I ask you for a confidence interval of people who are not married, then the p-bar value you'll be using isn't 0.3, but rather 0.7, okay? So let's follow the steps. If you scroll down to the page on, this is a one prop question. This is a one proportion question. You're going to be given steps for rejection region and confidence interval. Again, I implore you, do not look at the steps for a rejection region. I'm not asking you to do a rejection region just yet. I'm just asking for a confidence interval thing to start. So steps for a confidence interval. Step 1 is that it's automatically Z. I'll type this word because the word automatically is a long enough word that I can type it. Automatically Z. So we don't even need to do step 1. Step 2 says, okay, if it's Z, then you need to get your hands on the Z value. We want I think it's a 95% confidence interval, 95, say 0.95. So we need to get our Z score. That'd be inverse norm of 1 plus 0.95 divided by 2. And that gives me 1.96. I just happen to know the 95%. I'm sure that some of you are doing enough problems that you just recognize that the 95% confidence interval, if you're doing inverse norm, is going to give you 1.96. It's a very common answer. Now that we have that, I'm going to construct the confidence interval for the percentage of people who survived. So I don't want this value. I want 1 minus this value, which would be 0.618. Just pay super close attention to that because they're not asking for the percentage of people who died. They're asking for the percentage of people who survived. So this is my p-bar now, or p-hat, whatever you want to call it. I call it p-hat, but she calls it p-bar. We'll call it p-bar for today. And we'll plug these things into the formula. So it starts off with p-bar minus z times giant square root p-bar times 1 minus p-bar over n is less than mu, not mu, p is less than p-bar plus z times giant square root p-bar times 1 minus p-bar over n, close parentheses. We have all these things. So 0.168, this is going to be doing a lot of heavy lifting here. That's going to go here and here and here. And our value of n is that 14,413 that's going to go here. And our value of n is 1.96. Sorry, my value of z rather is 1.96. That's going to go here. So plugging all these things in, I get 0.618 minus 1.96 times, or 1.96 times the square root of 0.618 times 0.382 divided by 14,413, 0.61, almost on the dot, so we'll say 0.610. And then when I do it again, but plus, I get 0.618 plus 1.96 times square root of 0.618 times 0.382 divided by 14,413. And this gives me 0.626. And that is my commonest interval. And again, you can put notation around it. Again, this is going to be on Canvas. So she's going to say, what's the lower bound? You say 0.610. She's going to ask, what's the upper bound? You say 0.626, and you're done. Let's look at part B, which is using the rejection region approach. It's a little bit weird because we haven't at all, at least for those of you who have been coming to the quiz sessions, we haven't at all talked about the rejection region approach. Everything we've been doing up to this point has always been confidence intervals. So how does a rejection region approach differ? The steps are very similar. You first need to identify, so this is part A. But I want to juxtapose part A with part B and say, what are the steps here? Step 1 says it's automatically Z, still automatically Z. In fact, I'm just going to drag him over here. Still automatically Z. Step 2 says you need to get the Z value. The way we do that depends on whether the test is left-tailed, right-tailed, or two-tailed. So we have to actually first ask ourselves, what are the hypotheses for this test? So let's start by saying, reading through, use the rejection region approach to test the null hypothesis that the true survival probability is 0.6. So say H null, the true survival probability, so P, is 0.6 against the null hypothesis that it is not. So that would be H sub A, P not equal to 0.6. Okay? What tells you whether the test is left-tailed, right-tailed, or two-tailed? Because that's what we have to do in step 2. Step 2 says you're going to do one thing if it's a left-tailed test, you're going to do a different thing if it's a right-tailed test, you're going to do something totally different if it's a two-tailed test. Well, the type of tail of the test you can tell is based on the alternate hypothesis. So if you see HA colon P greater than 0.6, that's a right-tailed test. If you see HA colon P less than 0.6, well, then as you can probably guess, that's a left-tailed test. And then we have the one remaining case, which is the one we're dealing with. If we see P not equal to 0.6, then it's a two-tailed test. So we get a two-tailed test. That means we're going to be using that third column in step 2, which says that when you go to get your z-score, you're doing inverse norm, you're doing plus or minus inverse norm of alpha over 2. Let's talk about what alpha over 2 is. I said inverse, but it needs to be inverse norm. Alpha over 2. Well, alpha is the significance level, and that will also be stated in the question. So what is alpha? Alpha is the significance level. And it's denoted by what looks like to be a backwards fish. That's an alpha. In our case, I say backwards fish. No fish is neither forward nor backward. That's a downward fish. That's a rightward fish. So I say backwards. I don't know why it's backwards, but it's a fish. It looks like a fish, right? So alpha is a significance level. They say at the 0.05 significance level. So in our case, alpha is 0.05. You are going to do inverse norm of 0.05 divided by 2. And you're going to take, because this is a two-tailed test, notice that the two-tailed test has this plus or minus sitting out in front. So we want both the positive and the negative version of this. When we do this, I get one z-value to be negative 1.96, and I get another z-value to be positive 1.96. So we're going to use both of these z-scores. We'll get there in just a second how we use them. Step 3 has us find what are called the critical values. So this is step 3 says find the critical values. The critical values in this case are we find those by using the formula z equals CV minus H null value over, actually I'm gonna stick with P for now. CV minus P over square root of P times 1 minus P over N. And here, P equals the H null value. So I want to highlight one key difference between the rejection region method and the Commonest interval method. Notice that inside this giant radical, we see P and P. We don't see P bar as we saw for the Commonest interval method. For the Commonest interval method, you use P bar, but for the rejection region method, you use P. So I want to highlight that difference one more time. Let's do green. P and P versus P bar and P bar. We use P bar for the Commonest interval. We use just regular old P for the rejection region method. So that's just something to bear in mind. Okay. We have, yeah, what do I mean by H null value? Well, it's the value you can find in the null hypothesis. So where is that? That is this guy, 0.6. So we have Z, which is, we'll start with the negative version, 1.96 equals CV, we don't know. After all, you're trying to find the critical value, so we're trying to solve for CV, minus 0.6 over square root of 0.6 times 1 minus 0.6, that would be 0.4, and then divided by our sample size of 14413. Okay, I'm gonna go and solve that real quick. Be very careful how you type this into a calculator. A lot of people screw this up because they just typed in the number incorrectly or they don't know how order of operations works, but I can't help you with that. And then say plus 0.6. This is going to be 0.592. Hi, Victoria, she's back. Okay, cool. 0.592. This we're going to call, we have to get, this is one of critical values, but if you'll notice the little note at the bottom of step 3, it says, if this is a two-tailed test, which this is, right? We know it's a two-tailed test because this is a not equal to. We need 2 critical values. So this is CV1. And then CV2 will be the other guy that we get, which I bet you if we solve this, we're going to get, I know exactly what we're going to get. We're going to get 0.608. So again, how am I doing that? I'm just solving this equation for CV. I'm plugging in all the different values of P and N and Z that we know. So as to say, we found Z to be negative 1.96 and positive 1.96. We know P to be 0.06, or not 0.6, but 0.06, but 0.6. And we know N to be 14,413. Taking those values and plugging them into this formula here and solving for CV gives me 2 different values because, of course, we have 2 different Z values to use. We get 0.592 and 0.608. Step 3 takes a long time. Now we're going to move on to step 4. I'm going to make some room over here on the right. As we go into step 4, we ask ourselves, what is the rejection region? So the rejection region starts off by saying, RR equals. And again, the rejection region will depend on whether or not the test is left-tailed, right-tailed, or two-tailed. Well, we already established earlier, this is a two-tailed test. So it's going to be of the following form. It's P hat, or P bar, less than CV1. In our case, CV1 is 0.592. Or P bar greater than 0.608. I believe I mentioned this underneath step 4, or like where it says step 4, construct a rejection region, I think it says leave P bar as a variable. So we're leaving this as a variable. I know it might be tempting to take our P bar of 0.618 and plug it in for P bar right now, but when you construct a rejection region, you leave this as P bar. Step 5 is to draw a conclusion. So our rejection region is constructed. Here's how we draw a conclusion. If the actual value of P bar satisfies an inequality, not both, but one of the inequalities in the rejection region, then we reject the null hypothesis. Otherwise, we accept the null hypothesis. So as a reminder, what is our value of P bar, Victoria?
0.618.
0.618. We're going to take this 0.618 here and check to see if it satisfies one of these inequalities. Is 0.618 smaller than 0.592? No, it is not. Is 0.618 bigger than 0.608? Yes, it is. So with that in mind, we're going to reject the null hypothesis.
Perfect.
Cool. Let's see, there's one more question here, part C. This is a very common question that is asked. I'm going to clear all this, so knock this out of the way. A very common question is, for this for this problem, let's do this all bigger caps. Where's my format? There it is. For this problem, would the conclusions drawn by using the confidence interval method and the rejection region method necessarily be the same? The answer for a one prop question is always no. Let's talk briefly about why. Generally speaking, or maybe not generally, in specific cases, the rejection region method and the confidence interval method do the same thing. So if you reject the null hypothesis with the rejection region method, then you should end up rejecting the null hypothesis with the confidence interval method. They should lead you to the same conclusion. That's not necessarily true for the one proportion version. The reason is as follows. Remember how I highlighted earlier that the values of P and P bar are slightly different, or at least just in this guy alone? I want to kind of clear everything away. This is all a giant mess. We don't need any of this. What I'm just trying to drive at here is this here and this here. Okay, with all this, I'm trying to peel everything away. I don't need any of this stuff. The confidence interval method, in its measurement of like what's called the standard error, we use P bar here, right? Whereas in this formula, we use P. So there will be mathematically slight discrepancies between what the rejection region method will produce and what the confidence interval method will produce. And it's really only due to the fact that when you do the rejection region method, you use P inside this square root. And in the confidence interval method, you use P bar into the square root here. And because P bar and P are different, you might end up getting different conclusions. Rarely. They should very often coincide, that if you end up rejecting the null hypothesis in one case for the rejection region, you'll probably very likely end up rejecting the null hypothesis using the confidence interval method. But the question is it possible to get two different conclusions? The answer is yes, simply because we're using two different variables to construct this square root term. Cool?
I had a quick question.
Sure.
I remember in her lecture, she mentioned that the true variance is when it's not P bar, it's just P.
Yes.
So what is in general, should we take it as the variance of the proportion is P times 1 minus P over N?
Yep.
Okay.
And the square root of that, or yeah, oh yes, without, if it's a variance, then it's not being square rooted, correct.
Okay, thank you.
Yep. And so the discrepancy is that here, we don't know the true value of P, because after all, we're constructing a confidence interval for it. So we have to just go based on what the sample proportion is. Whereas here, when we're doing the rejection region method, well, we're already assuming that the value of P is known, and we're assuming that it's known to be 0.6. Okay. That's a one prop question. We're going to do a one variance question, and that would be number 7 from summer 2019. Let's see if it's even worth doing. Summer 2019. Number 7. And this is going to be a one variance question. In parts of the world where attendance at school is erratic, educating children in higher grades is difficult because there is considerable variation across children in the preparation they bring for lower grades. An economist in a developing country wants to measure the variation. So that's kind of one thing to point out, is that the economist wants to measure the variation in preparation for grade 5 by looking at dispersion of student scores on a standardized test beginning at grade 5. She takes a random sample of 31 students. So I'm going to go ahead and snag that. N equals 31. Let's do this in a different color. N equals 31. In this sample, the standard deviation is 57. I'm going to make up a score, by the way, for the mean score. This was not given, but she can give this to you and make it seem like this is something you need, but we're not going to actually use this. And they say the sample standard deviation is 57. So again, at no point in this problem did she say anything about a sample mean, but I'm saying she could have said something to make you think you need to use this, but because this is a one variance problem, we do not need to use the sample mean. It will not actually come into play at all for this problem. Okay, let's go back over to continue what they want. They want, oh, test scores are approximately normal. So that's another important part, is that test scores say approx normal, although it doesn't really change the answer to the first question, which is that we're using the chi-square distribution. But we'll talk a little bit about this. Approximately normal. And now we want to create the 95% confidence interval, so 0.95. Okay. So let's follow the steps for the one variance page. Make sure you skip down. It's a few pages below the one proportion page. And those steps say, step one, it's automatically chi-squared. So automatically chi-squared. Because it's a one variance question, it's automatically chi-squared distribution. Step two says we need to get our two chi-square values. So we need to get chi-square lower and chi-square upper. There is a calculator program that I've shown how to write. I think I've put it in a YouTube video somewhere in the GroupMe. If you want to see it again, just at me in the GroupMe and say, hey, Andy, can you show me the way to program my calculator to do it? It can be tedious, especially if you're not familiar with how to program a calculator, but I make sure that you can see every button press that I do in the video so that you can do it even on your own TI-83 or 84. Okay. If you don't have a TI-84, or rather if you don't want to use it or learn how to program it, that's fine. You're going to need to then reference a chi-square table. So I'm going to go grab a chi-square table from the internet. I think that the reason we got into some trouble with, I think for those of us who were working on questions 16 and 17 on the previous quiz had an issue with that because I probably used a table that didn't go to as many decimal places as we needed to. So some people had some issues with that. But if you go to one with enough decimal places, or if you just use the table that she provides to you in Canvas, then you can't go wrong, because I'm sure that when she's constructing her problems and her solutions to these, she's using the chi-square table that she's provided to you. She would never use a table that goes to more decimal places when she writes the problems and then give you one with fewer decimal places. So we want the 95% Commonest interval. What we want to do is we want the one corresponding to 1 plus 0.95 over 2 and 1 minus 0.95 over 2. So you want the chi-square values that correspond to tail values of 1 plus confidence level over 2 and 1 minus confidence level over 2. So you're looking for chi-square values that correspond to 0.975 and 0.025. When I go to find these, I have to make sure we match it with the correct degrees of freedom. Our sample size is 31. So that means our degrees of freedom is 30. So on our table, we want the row corresponding to 30 degrees of freedom, and with the columns corresponding to both 0.025 and 0.975. 0.025 with 30 degrees of freedom is 46.979. This table that I have here, unfortunately, does not give me the left tail, so let's go find another.
I have it.
Do you do?
Yeah, it's 16.791.
Yeah, I just found it. I agree. 16.791. So these are my chi-square lower and chi-square upper. 16.971 and 46.979. Okay. To construct the commonest interval, you just follow these simple steps. You do n minus 1 times sample standard deviation squared, or sample variance, divided by the way, did they give me sample standard deviation or sample variance? Sample standard deviation, okay. So they gave me, this was S equals 57. We need to remind ourselves to square this. Divided by chi-square upper is less than sample, or the population variance. It looks like the ugliest U. I'm not happy about it. I get OCD about my letters. Okay. N minus 1, on this side, it's n minus 1 times S squared over chi-square lower. It's kind of confusing because you would expect, well, if this is lower, you would expect lower to be in the low end. You expect upper to be in the upper end. Yeah, but this is because when you go to construct this, you want this value to be lower than this value. And that can only happen if you use the higher value for chi-square here than here. If you divide by a big number, what you get is a small number. We have all of these values. We have n, we have s, we have our chi-square values. So we just plug these into our formula down here and we'll get an answer. Let me go ahead and do that. That would be 30 times 57 squared divided by 46.979. If we do that, we get 2074. I'm going to go to several decimal places. Let's see if I can copy and paste. Please let me. It did. Nice. Let's go to 3 decimal places. Okay. Then I'm going to do the same thing again and do 30 times 57 squared divided by my chi-square lower, which is 16.971. And you get 573 point, we'll round this to a 7. And this is your answer. This is your confidence interval. You might say something like less than, let's do a different color here, less than sigma squared less than. This is a 95% confidence interval, so you might see the answer presented like this. That's fine. Or what's more likely is, again, she'll just say, type in the lower bound, type in the upper bound, make sure you round to the appropriate number of decimal places. One other thing she might ask. I asked for, or this question was asked for, what is the confidence interval for the population variance? Is that true? Let's see if I'm even lying. Yes, calculate the 95% confidence interval for the population variance. But I could have.
Andy,
Yeah.
I think you got the wrong value for the 5,000 number. I got 5,804.894.
Sure. Let me double check that. 30 times 57 squared divided by my chi-square lower, 16.971. I get 5743.
16.791. Not 971.
Oh, 791? Oh, dyslexia has kicked in. Not 791. There we go. Okay, that'll make a big difference. So let's do that again one more time. 30 times 57 squared divided by 16.791, 5804, somewhere around that neighborhood.
Yes, that's what I got.
Cool. I'm gonna round that to 3 decimal places. Cool. Good catch. I'm just losing my mind. Did I 30 degrees of freedom? 791. Sure enough. Just wrote it down wrong. Okay. So that's our confidence interval. And then the follow-up thing I wanted to say is that she asked for what's the confidence interval for the population variance. We have constructed that. That's what we've done here. But she could have just as well asked for what? What is the confidence interval for the population what? What could she have asked, Victoria?
I want to say mean, but
nope. Well, what two things are more heavily tied together? Variance and mean, or variance and
standard deviation?
Right. So she could ask for what is the confidence interval for the population standard deviation? Well, what would I just need to do to my values?
Square root.
Right, exactly. So if I wanted the confidence interval for the population standard deviation, then you just square root this value, and you'd be done. Good. This is something she does commonly. She is also very nice that in that she bolds the things. So she knows that she's given you these things, and she knows that the formula usually that you've constructed here is for a population variance. So when she states her question, she'll say, what is the confidence interval for the population, and in bold, standard deviation. She's trying to help you out here because she doesn't want you to get the question wrong just because you misread it. But that's why it's all the more important to make sure you're reading the question carefully for, do they want the population variance or do they want the population standard deviation? With that in mind, we've done everything we need to for part A, which is to create that confidence interval for the population variance. Do we need to draw a conclusion based on that? Yes, we're not quite out of the woods with part A. So we are testing a hypothesis. We're testing the null hypothesis. Test the null hypothesis that the population standard deviation, so this is where a situation where she has once again switched from variance to standard deviation. So test the null hypothesis that the population standard deviation equals 40 against the null hypothesis, or the alternate hypothesis that it does not. So against alternate sigma not equal to 40. And what are the rules for this? The rules are if the confidence interval contains the null hypothesis value, then we accept the null hypothesis. All the way around, if the confidence interval does not contain the null hypothesis value, then we reject null hypothesis. Now, you might at first glance think, well, no way in hell does the confidence interval capture this value. But as a reminder, this is the confidence interval for the population variance. So we need to square this value, sigma squared equals 1600. You could either square root these values to make them a confidence interval for a standard deviation, or you can just square the standard deviation here and make it a variance. Is 1600 in this interval, Victoria?
No.
Nope. So we are going to reject null hypothesis because 1600 is not in the confidence interval.
Perfect.
Cool. Let's continue. Test the null hypothesis using that. We just did that in part B. Okay. Part C, so part B was just test that, or just draw a conclusion. So part A was construct the interval. Part B was draw a conclusion. I get a lot of people who, and this is important, the steps that are usually for a confidence interval are 4 steps long. It is step 1, determine the distribution. Step 2, determine the z values or t values or chi-square values or whatever. Step 3 is to construct the interval. And then step 4 is to draw a conclusion. Step 4 isn't always something you need to do, right? If the question had just merely asked you, as we've done this a few times already, just construct the interval, you wouldn't need to do step 4. You wouldn't need to draw a conclusion. So it's only when they ask you, when she asks you a later part, which is I want you to now draw a conclusion based on the confidence interval you created, do you then need to do step 4? So in our case, yes, the first 3 steps of the process to construct the interval are needed to do part A. And it's only then do we do part 4, or step 4, to help us do part B. Okay, so it's important to bear in mind. Some people say, Andy, I don't know how to do step 4. Well, sometimes you don't have to do step 4. Sometimes they don't ask you to draw a conclusion. Sometimes they just ask you to construct an interval and you're done. Okay, let's keep going. Now we want to do the rejection region method. I'm going to clear all this off, clear most of this off. We don't need any of this. I probably want to save some of that actually. Save this. Okay, don't need this or this or this. We probably want those. Do we want those too? We probably want those. It's going to be the case that some of the same stuff appears and it's going to make our life a little bit easier. Yeah. This is I think is all we need now. So we're doing the rejection region method, and I'm not even quite sure if I remember my own method for this. Where do I have my cheat sheet? There it is. So I'm going to go down to 1 variance, and we're doing the rejection region method. Step 1 says it's automatically chi-squared. Step 2 says get the chi-square values from the chi-squared table. That will be determined whether or not it's left-tailed, right-tailed, or two-tailed. Well, Victoria, is this left-tailed, right-tailed, or two-tailed?
Two-tailed.
Two-tailed. We see in our ultimate hypothesis the does not equal sign or is not equal to sign. So this implies that it is a two-tailed test. So what that, if it had a greater than sign, if it's greater than, that's a right-tailed test. If it's less than, it's a left-tailed test. In our case, it does not equal, so it's a two-tailed test. If it's two-tailed, we look up the chi-square values for alpha over 2 and 1 minus alpha over 2. As a reminder, they said at a significance level, of 0.05. So that means alpha equals 0.05. Guess what? That 0.05, when you go to look up the chi-square table values for that, you're going to get 16.791 and 46.979. So I don't need to relook those up again because, and you might have noticed a trend here. Previously, we just constructed the confidence interval for a 95% confidence interval. Guess what? The chi-square values that correspond to the 95% confidence interval correspond to the 5% significance level. And this kind of go hand in hand. We have 5% here and 95% here. I'm hesitant to say that alpha plus confidence level equals 1, but that's a trend that you are going to see very often. That in our case, the confidence level value was 0.95, the alpha level is 0.05. So adding those two things together give us 1, and we're going to see that's a common trend we're going to see. Don't always assume that that's going to be the same, and it's always worth double checking to make sure, is this indeed, I mean, if you're pressed for time, just go with the ones we have, but is it indeed the case that when I look up alpha over 2 and 1 minus alpha over 2 that I find these chi-square scores? It's sure enough, it is the case that I find those two. So I found those two chi-square scores. Now I'm going to do step 3. Step 3 says find the critical values by solving for CV. So the formula we're going to use here is chi-square equals n minus 1 CV over sigma squared. And this sigma squared is your H null value. So you might say, oh, Andy, I don't see sigma squared anywhere. I don't see sigma squared. Where's sigma squared? This sigma squared is your H null value. So you don't have to go looking too far for it because it's in your null hypothesis. So let's plug all these things in and solve for CV. It doesn't matter which one you do first, but we're going to do, this is one of our chi-squared values. We're going to start, you can start with 16.791, but then after you do that, you use 46.979. Okay, so I'm going to go ahead and solve for that. 16.791 times 40 squared divided by 30, and I get a critical value of 895.52. That's one of my CVs. It might be CV1. It might be CV1 or CV2. I'm going to denote them after the fact. I usually use CV1 for my smaller CV. I use CV2 for my higher CV. Now I'm going to do chi-square again, but now I'm using this value for chi-square. 46.979 times 40 squared divided by 30, and I get 2505.55. That's fine. 2505.55. Well, the first value is clearly smaller, so this is CV1, and this is clearly larger, so this is CV2. We're going to proceed now with step 4, which is to construct your rejection region. Rejection region always starts off with RR equals. And in this space, you're going to use S squared. And it's a two-tailed test, so it's going to be S squared less than 895. Remember, leave S squared as a variable. Or S squared greater than 2505.55. Last step is to draw a conclusion, step 5. That conclusion is drawn based on whether or not our sample standard deviation, which was this guy way back up here, satisfies one of the inequalities down below. So let's go ahead and take S squared. Let's get that. First things first is S squared would then be 57 times 57 is 3249. Does 3249, is 3249 less than 895? No. Is it bigger than 2505? Yes, it is. So because of that, if S squared satisfies, go ahead, Victoria.
Yeah, we reject because it's intersection region.
Yep, if S squared satisfies one of the inequalities in our rejection region, sometimes you're going to have just one inequality because it might be left-tailed or right-tailed. But in our case, it has two. If it satisfies one of the inequalities in our rejection region, then we reject the null hypothesis. Sometimes on the test, you're just going to have what conclusion do we draw? And you literally have, I don't even think she has answer choices. You might think it's multiple choice, but it's all fill in the blank. So she says type A if you reject, type B if you accept. Cool. So for our case, we're going to type A. That would be our answer. Let me look at, I think there's one last question. What is the power of the test? We're not going to talk about power today. Power will be something different, but the most important part is that today, so far, we'll do a little bit more because I want to see if we can do some one-sided confidence intervals if possible. We have done one variance. Let's clear this whole thing. So we've done one mean, one prop, and one variance. And in fact, we did rejection region and confidence interval methods for both one prop and one variance, I believe. I don't think we did any rejection region method for one mean. We just did confidence intervals, but that's fine. We also did a minimum sample size from that as well. I do want to spend a little bit of time because I said, what did I say part 1 was going to cover? So the one mean, one prop, one variance stuff, but I also wanted to talk about one-sided confidence intervals, p-value, and minimum sample size. I'm going to see if there are such questions on this test. Let me give me a second to find that because I'm not quite sure if there is on summer 2019. I want to double check to make sure there are. It would never tell me in my breakdown. My breakdown doesn't really tell me that there is. Minimum sample size, I guess there is for question 6. Let me just skim through here. I don't really spend too much time on p-value. I'm going to do it a really, really quick problem because usually there is only one question on the entire exam, which is about p-value. It's there. It's part D, number 3, part D. So we're going to look at, see if I can do this. Summer 2019 still. Number 3, but only part D. I'm not going to do too much of this problem, which would just do the p-value part. Cool. It's continued from part C, so I'll say part C and D. For a particular well, the operator wants to test the null hypothesis that the true pressure gradient is at least 70. So H null, colon, she wants to test the true pressure gradient, so this is a mean, is at least 70 against the alternate hypothesis that it is less than 70. So that is what's stated in part C. This is what part C says. To test the null hypothesis, the operator takes 9 measurements. So n equals 9. That's our sample size. And we want to control the probability of a type 1 error at 0.01. So control, actually probability of type 1 error, that's better known as alpha, right? We've also called it significance level as alpha. These all go hand in hand. So if you see significance level, that means alpha. If you see probability of type 1 error, that means alpha. So in our case, she has stated that she wants alpha to be 0.01. You do not need to require blah, blah, blah. What rejection should be used? The sample mean is 67. I think we also need to reference, we might have to reference the very beginning of the problem where they say the variance is 9. And actually it says, assume that measurements are approximately normal. So approximately normal. And we have population variance, sigma squared equals 9. Population variance is 9. Okay, good. So you're going to scroll down to the section of my cheat sheet which says finding the p-value. It's the first page, I think it's like very top of page 4 or 5. So it says finding the p-value. Step 1 says compute the z-score or t-score, and again use the tree to determine whether or not it's z or t. So the first question I ask myself to determine whether or not it's z or t is the population approximately normal? Yes, it was stated to be approximately normal, so that part's done. Is the population variance known? Yes, the population variance is known. So we have both of these things, the approximately normal and the population variance or population standard deviation is known. So with that in mind, we're going to be using z. So to continue step 1, we're going to find, compute the z, or step 1, find the z-score. Z-score is found by using one of those 4 formulas, depending on if it's a 1 sample mean or a 2 sample mean or a 1 proportion or a 2 proportion. This is not a proportion and it's not a 2 sample mean. This is a 1 sample mean, which is one group. It's only one group we're testing, and we're gathering numerical data rather than percentage data. So with that in mind, we're going to use the formula z equals x bar minus h null value over standard deviation over square root of n. This time we're finding z. We have x bar. Damn, I didn't write it down, did I? I did not. X bar was stated to be 67, I believe. X bar is what? Oh, do I want to do part C? Not really. Part C wants to have us make a rejection region, but the steps for making a rejection region, we've done that a couple times now. We're just gathering all the information we need from part C. So I'm skipping part C. I'm only grabbing the p-value, which is in part D. I had to look at part C though to get all the information I needed and the paragraph at the top of the page. So X bar is 67. We're going to punch all these numbers into the z-score value over z-score formula over here. So we have 67 minus your h null value. Your h null value is 70 divided by your standard deviation. Be careful. Your standard deviation is not 9. It's the square root of 9 because this is a variance. So we get 3 over, and then our sample size is 9. So we have square root of 9 here. And this gives me, go ahead.
So the 70, which comes from like the h null value, would it have mattered if the h null had just been greater than, like strictly greater than, or
Nope.
equal to? Like,
Nope. Nope, same result.
So it'll always do that.
Yep, and very frequently she only uses greater than or equal to, less than or equal to, or equals for this. For the alternate hypothesis, it's either less than, greater than, or not equal to.
Perfect.
There's one rare instance where it's equals for alternate, but very frequently it's one of these. Well, I shouldn't underline them, but it's one of those 3. The equals part usually comes in the case where we're doing some drawing, where we're going to be asked to draw some graphs, which will be a different lesson for a different day. But yeah, So these are the three most common results for null hypothesis and the three most common symbols we'll see for alternate hypothesis. And yeah, had she not used, had it still, even to answer your question theoretically, even if we didn't have the or equals to here, it still would have been 70 in our z-score calculation. Okay, so we got -3. And now what do we do with that value? So this is where step 2 comes into play. It says compute the p-value using those formulas. It says if it's a z-distribution, use normal CDF. If it's a t-distribution, use t-CDF. Well, we've already established that we're going to be using the z-distribution because of it's approximately normal with a known population variance. And then we ask ourselves, is it left-tailed, right-tailed, or two-tailed? Well, in our case, what tail test is this?
Left until left-tailed.
Yep, this is a left-tailed test. So because it's a left-tailed test, we're going to be using normal CDF -100 comma our z-score. So normal CDF -100 comma -3. If you do this, you're going to get a really tiny p-value, something like 0.0015-ish. You can correct me. It might be 0.0017 or 0.0013.
13 is what I got.
That's what I thought. But really small. And then we draw a conclusion. Do they ask us to draw a conclusion? They don't. But if they had to draw a conclusion, the rule is as follows. To draw a conclusion from a p-value, we use the phrase, if the p is low, reject the ho. And by ho, we mean null hypothesis. Okay? So what counts as low? So low here means lower than the significance level, aka alpha, significance level, aka lower than alpha. So as a reminder, Victoria, what was our alpha level?
0.01.
0.01. Is our p-value lower than that? 0.0013.
Yes.
Yes. So because our p-value is lower than 0.01, we are going to reject the null hypothesis. So because our p-value, 0.0013, is less than alpha, which is 0.01, we reject the null hypothesis. They didn't ask us to do that or state a conclusion based on the p-value, but that's what we would have done if we were given an answer choice based on p-value. Good?
Yeah.
I think we probably have time for a little bit more doing a one-sided confidence interval. Let's suppose that we were asked to create a one-sided confidence interval to test this hypothesis. So how do I do that? I think that's still on the p-value page. So we're going to construct a one-sided confidence interval. So all this stuff over here, by the way, all of this junk, this was our work for p-value. And now we're going to do, over on this side, a one-sided confidence interval. Step 1 is it z or t? One more time, we've already established that we're going to be using the z distribution, so we're going to continue that. We're going to use z. Let's suppose I wanted to create the 95% confidence interval, but again, the one-sided confidence interval. Do they have you? Sure, 95% one-sided confidence interval. Actually, let's not do that. Let's say testing using the same level of alpha. So we'll say alpha is still 0.01. So we'll say alpha equals 0.01. What do I want to do here? Yeah, we'll leave it as 95%. Because when you're doing a one-sided confidence interval, they could either provide you with a level of sigma, or not sigma, alpha, or a confidence level. We're going to say a 95% confidence level, but just be wary of the fact that I've given you formulas for both what you should do if they provide you with a confidence level versus if they provide you with a significance level. So just be mindful of that. This time I'm going to say use the 95% one-sided confidence interval. So we'll be doing that. Step 2 says get z or t on that basis. We already know it's a z, and we're going to be using confidence level, so we're going to do inverse norm of 0.95. What is inverse norm of 0.95? I think it's 1.645. 4, 5. 95% normally is 1.96, but this is a one-sided confidence interval. So we actually don't get the 1.96 that we would normally expect with a 95% confidence interval because, again, this is a one-sided confidence interval. Okay, step 3, we've already got our z-score. Step 3 means construct our interval. What's weird about these one-sided intervals is that they have infinity, or negative infinity as one of the bounds. And which interval you use depends on whether your test is left-tailed or right-tailed. Well, as a reminder, our test is left-tailed, so we're going to use the left-tailed section of our confidence interval. That means it's going to start off with c, open parentheses, negative infinity, comma, or not comma, we'll say less than mu, less than x bar, which was, that was way back here, 67, plus z, which is 1.645, times our standard deviation, our sample standard deviation, which is, or not sample, but population standard deviation, which is 3. Careful, don't assume that it's 9. We know that sigma equals 3 here. Divided by square root of 9. And this gives us 67 plus 1.645 times 1. So we get negative infinity, comma, mu, less than 68.645. This would be the one-sided confidence interval that for this test. And that's it. Do they ask us to draw a conclusion? You could. Got it. I even put a note here. One-sided confidence intervals can be used to test left and right tail hypotheses, but two-sided intervals cannot. So that's a really important note to make, is that if you have a left or right tailed hypothesis, you cannot use your regular two-sided confidence interval. You have to use a one-sided confidence interval to draw a conclusion. So you could, for instance, draw a conclusion here. What is the conclusion we would draw? Well, what's our null hypothesis value, Victoria?
70.
70. Is 70 in this interval? No. So because of that, because 70 is not in the confidence interval, we reject the null hypothesis. We seem to be doing a lot of rejecting today, but sometimes you'll end up accepting.
Okay.
All right. I think that wraps up everything I wanted to cover. We did one minimum sample size question. We did it for a mean, but we've also done some minimum sample size questions for proportion. The formula is very similar. We did a one-sided confidence interval. We did p-value, and then we also did the, as we said before, one mean, one proportion, and one variance. And that's really going to wrap up the first part today. Go back and revisit some of those problems. If you have any questions, you can ask me anything you want. But I'll see you guys next time for part 2, where I start talking about 2 mean, 2 proportion, and 2 variance problems, along with some other odds and ends. I'll see you guys then.